So let me introduce my friend and colleague, Dr. Sanoop, who is the next speaker of our talk today. Dr. Sanoop is an assistant professor in the Department of Chemistry at Madanapalli Institute of Technology, where he has been serving since 2023. He earned his PhD in Chemical Sciences from CSIR and NIST Trivandrum with registration at the University of Kerala in 2023. Following his doctoral studies, he worked as a senior project associate at CSIR NIST. In recognition of his academic excellence, he was awarded the State Government Research Fellowship in 2017 and secured a top rank in MSc Chemistry from MG University, Kerala in the same year. Dr. Sanoop's research focuses on engineering nanostructured surfaces and colloidal nanoparticles for SERS substrate, surface enhanced Raman scattering, substrate fabrication, developing plasmonic SERS substrates for disease diagnosis, applying Raman spectroscopy analysis to food products, utilizing multivariate analysis and software tools for qualitative and quantitative estimations, and synthesizing electrophotocatalyst as well for hydrogen evolution through water splitting. He has published several research articles in reputed peer-reviewed journals. I welcome Dr. Sanoop to present his lecture. Sir, the stage is all yours.
Thank you, sir. Thank you very much for your kind introduction of words. And thank you for the organizing committee to give me a chance to present my research work in this conference. So I will share my slide. So thank you very much. So myself, Dr. Sanoop, Assistant Professor, the Department of Chemistry. So today talk is all about developing Raman and surface enhanced Raman spectroscopy methodologies for food and disease diagnosis. Here I'm taking some specific examples for food and disease diagnosis application while using Raman and surface enhanced Raman spectroscopy technique. This is actually one piece of work in my PhD. So this is in this presentation I'm going to present so the simple things regarding the introduction regarding Raman spectroscopy and surface enhanced Raman spectroscopy and how we can find their application in the food diagnosis and disease diagnosis by taking by some particular example or specific example. So coming to Raman spectroscopy, as we know that when it is a vibrational spectroscopy technique that is working on the principle of inelastic scattering of light. So here the instrumentation part we will discuss later in the coming slides. We will discuss this one. The instrumentation part, we can see that when whatever the general part, we have a spectroscopy technique, that is a light source and the probe optics and detector. Generally we are using the light source as lasers, either 533, 633 or 785 based on their applications. Suppose if you are using the biological application, we are going for low laser or low energy lasers. If you are going for material analysis, we are going high laser like 533, 633 lasers we are using. And why Raman spectroscopy has some advantages over other spectroscopy technique? That the first thing we can mention that it is a non-destructive technique. That is one of the thing, and also compared to other spectroscopic technique, for example, in the case of IR, or if you are going for the like mass spectrometer, we have to go for some sample preparations. So here we know in some cases only we need some small sample preparation techniques, and also this technique will provide the fingerprint information. And in comparison with the IR spectroscopy, we can see that even Raman spectroscopy having very less interference, or we can say a negligible interference from water. So that is one of the key reason that why Raman spectroscopy using more in the biological applications. So if you're discussing the advantages of Raman spectroscopy, even though it's having some challenges, that some limitations having. For example, if you are considering the cross-sectional area of Raman, IR, and fluorescence, here we can see that when the Raman having very low cross-sectional area. So what we can say here if you are in about 10⁶ photons are incident on a surface, we can see that even among that only one photon is actually going to the inelastic scattering. So that will leads to we have to use some high laser power, extremely sensitive detector, or large instrumental cost. So to avoid this limitation, to overcome this challenge, there are another method that is called the surface enhanced Raman spectroscopy technique that is actually invented by Fleshman and his co-workers in 1974 that they observed the pyridine molecule when they interact with the nano surface, mainly the nanoparticle, the Raman signal is suddenly increasing. The intensity of Raman signal is suddenly increasing. The only it is happening when the particle is interacting with the nano surface. So that is mainly due to one of the important optical property of nanoparticle that is called the SPR, surface plasmon resonance. So why some of the molecule or the molecules when interacting with the nanoparticle, why the intensity or Raman intensity is increasing? That is mainly explained by two mechanisms. That is one of the mechanism is called electromagnetic enhancement and other one is called the chemical enhancement. The electromagnetic enhancement is purely based on SPR. This is a property associated with the nanoparticle. So the intensity of electric field of the light, whatever the light we are giving, the laser source, that is enhanced. In the second case is chemical enhancement. That is actually the charge transfer. The charge transfer from the metal nanoparticle to the analyte molecule or vice versa. So these are the two important mechanisms why these molecules showing higher intensity when it is contact or when connected with the nanoparticles. If you are discussing the surface enhanced Raman spectroscopy, SERS, it is mainly important to discuss the SERS substrate. SERS substrates means either we can see in a colloidal, simple colloidal nanoparticle, we can use it as SERS substrate, and also solid-based SERS substrates are available. So the preparation techniques, we can divide into two approaches. That is generally used for the preparation of nanomaterial. That is, one is the bottom-up approach, and another one is the top-down approach. The more importantly, if you are preparing any SERS substrates or this plasmonic substrate, we are using some plasmonic metal like silver, gold, and copper. The major point, the ideal characteristics of a plasmonic substrate, that it should show better reproducibility, uniformity, and good enhancement factor. And the fabrication process is very simple, and their stability, sensitivity, all are we have to concern when we have to go for a better or ideal SERS substrate. So the applications of Raman and SERS, we can use this method in vast area like their food, beverages, pharmaceutical, narcotics, explosives. There is plenty of application we can observe in the case of Raman and surface enhanced Raman spectroscopy technique. But in this talk, I'm going to discuss the analytical aspects, or we can say the disease, diagnosis aspects of Raman and the surface enhanced Raman spectroscopy technique. So by taking some food items, for example, here I am taking a specific example, edible oil, how these Raman spectroscopy we can apply with the help of some chemometric tool, or we can say the multivariate analysis tool. And also in the second part, what I am doing, I am fabricating one SERS substrate especially for the creatinine sensing. That is one of the application, that is disease diagnosis using SERS substrate. Here I am mainly detecting or quantifying the creatinine in artificial urine sample. So coming to the introduction, the first part, the application of Raman spectroscopy for food diagnosis. So as we know that I took one example as edible oil only. So why I took edible oil? Because we know that edible oil is actually the triglycerides it's a triglycerides of fatty acids. So we know that it contains so many fatty acids like lauric acid, oleic acid, linoleic acid, and its advantage like we know that it's essential for human diet and source of energy. It's contain antioxidant, omega-3 fatty acids. So the problem is associated with this edible oil. We are doing the process of adulteration. So not only in the case of edible oil, most of the food products now we can see that one is adulterated. So the problem is the adulteration. So the other important thing is that in edible oil, if you are considering the edible oil, some of the quality parameters or analytical quality parameters, that is also very important. For example, if you are considering the quality parameter of edible oil like iodine value, saponification value, acid value, peroxide value, you can see here why these values are important. So for example, in the case of iodine value, it is actually measures or giving the measures of how much degree of unsaturation is present in a particular fat or oil. If you're considering the saponification value is actually what is the molecular weight of the fatty acid present in the fat and oil. So in this work, my motivation is actually still now some food safety standard authority officers, or we can say they're using some kind of conventional method like titration. So here you can see that one they're using some iodometric titration like called WIS method, and some Hubble method. These all are the titration methods. Still, they are following in the conventional method. This conventional method still they are following in the laboratories. So For example, if you are going for the eigenvalue is actually, I already mentioned that even it is the measure of total unsaturation present in the edible oil. If you are going for the eigenvalue, you can see that even they are using some chemicals like the use of toxic and toxic chemicals like iodine monochloride. Then one of the most dangerous and also is a corrosive chemical. So most of them using this kind of conventional titration method for analyzing this parameter, quality oil parameter. So my concern is here unsaturation. They are going to evaluate their unsaturation, or they are going to measure the unsaturation present in the edible oil. So why I can use the spectroscopy technique for determination of this same unsaturation or their acid content present in the oil. Okay. So that is my concern and that is my motive. So for that purpose, what I did here, I focus on the eigenvalue. Eigenvalue, I already mentioned that one. This is the tool that is actually measure the total unsaturation present in the oil, and also it's a better authentication tool. So here, the first method is actually, you can see that even that is actually the Timble iodometry method that they are using. Which method? Okay, here you can see that the iodine monochloride that they are using. I already mentioned the side effects of iodine monochloride. So my concern is actually here, I am using two different model system. So the point is that the model system one should have very least iodine value and other one have higher iodine value. Then I can estimate the remaining edible oils within the range of the lowest and the highest. That is my concern. So for that I took coconut oil and sunflower oil. That is here mentioned CO and SO. So you can see that even the iodine value present in each oil. So from the GCMS analysis also we can see here, in the case of sunflower oil, you can see the linoleic and the first one, linoleic acid and oleic acid, the composition, their percentage is higher, which means their unsaturation level in the SO is very higher. So the same thing I applied in the Raman spectroscopy analysis also. I took the Raman spectra of both CO and SO. Here you can see that one. If I am adding more amount of SO, which is from sunflower oil to the coconut oil, you can see that one. There is a gradual increase in the unsaturation level. So if you are seeing the Raman spectra or spectral analysis of this edible oil, the peak at 1658 is actually corresponds to the how much unsaturation, which means the double bond present in the oil, and the peak at 1442 that is corresponds to the saturation present in the oil. So my point is very simple. Why I can make some algorithm based on this analysis. For example, one is the unsaturation level, other one is giving the saturation level. So here you can see that one. If I am continuously adding SO to the CO, you can see the peak at 1658, that is corresponds to unsaturations keep on increasing, but the saturation level is almost constant. So the next level, I plan to make an algorithm that is we have to implement in some software. For that purpose, I draw two graphs regarding the first one is the concentration of sunflower oil against the iodine value that we are determined using the standard method, that is a WITS method, and the second one I plotted the graph with the concentration of SO in CO against the peak intensity or peak intensity ratio, that is the saturation to unsaturation to saturation level. Here you can see that one. Here we have made two relationship based on the first graph and second graph. In the first graph is actually the iodine value, that is we are connected with the concentration. In the second graph we are connected the peak ratio with the concentration. So if we are going for the third equation, we can see that even the first equation and the second equation, from the first and second equation we are giving one more equation, that is actually how this iodine value directly connected with the peak ratio. Here you can see that even this iodine value we can directly connect with the peak ratio, and we are calculating is a basic straight line equation only, and we are calculating the slope by using the first two equations. So my next aim is actually how I can implement this relationship in a software. That is my next concern. Here you can see that one. Here for implementing or development of this algorithm, I use the LabVIEW software. So as a chemist, we can see that we know that one. If you are going for some MATLAB or Python or R software, we need some kind of programming knowledge. But in the case of LabVIEW, why I prefer LabVIEW means here it is very easy to use because we are using some kind of what we are called is a blocks only. Okay, suppose if you want to draw a graph, you can take a block, like a graphical block. Okay, so it's very easy to operate the LabVIEW software as a chemist. Okay, so here I developed one algorithm. I developed that algorithm in the LabVIEW software. For that purpose, what I did, I want the peak intensity from both 1658, that is the unsaturation as well as saturation, and I want to take the ratio also. This is because I want to incorporate the linear relationship in this graphical algorithm. So for that purpose, and also I am incorporating the baseline correction software, or we can call that as a background subtraction into the algorithm. So here you can see that one, if you are loading the data, so next level, what happens, it will undergo the background subtraction and they are taking the intensity from unsaturation as well as saturation, and finally they are calculating the ratio, and there finally we are based on the equation, they are calculating the eigenvalue. So this is one demonstration. Actually, here you can see that one, how this is working. Suppose this is the Raman spectra. I am taking one edible oil. I am taking here. You can see that one. This is the Raman spectra. So this is our developer software. This is very simple to operate. Actually, this is the GUI. The background I already mentioned that one. We are taking the peak intensity of saturation to unsaturation level. So this is the very easy. This is very easy to operate. Also, if you are uploading the data from here, you can see that one. Okay, I in the form of text file or CSV file, you can upload the data, Raman data of different edible oil, and based on the algorithm, you can see the value also. So here I am uploading the data here. So whatever the available, whether it is a mixture of oil or is a separate oil, we can upload the data here. And if you're running the software based on the algorithm, it will show the value on the screen in the GUI. So very simple here. Within, I already mentioned that one. Conventionally, still they are following some conventional method like titration, but in this method, within 2 minutes, for 1 minute for the Raman spectral for taking the Raman spectra, and 1 minute for the entire analysis. So within 2 minutes we can finish all analysis. So that is one of the most important advantage of whatever the developer method here. So the next level, we have to validate the developer methodology with the available one. For that purpose, we took some different types of oil, and also we took different concentration of oil with the SO and CO, and we predicted the eigenvalue with our software as well as our WITS method, the standard method. So we can observe here most of the values are aligning here, and also we calculated the eigenvalue of some blind sample, and also estimated some of the statistical error parameter. So all of them is revealing the method is a good precise method, and also we determined some of the eigenvalue of different oil more than the CO and SO. So here you can observe that. Here you can observe that most of the values relays the literature reported value. For the next level, we calculated or we estimated the intraday precision, how these values are changing in a day, how these values are changing between the day. So there are no that much changes in the values, and also we calculate the LOD and the LOQ. It is around 1 gram per 100 gram oil, and also 3 gram per 100 gram oil respectively. And the matrix effect is actually how these analysis varying with if you are changing the Raman analysis parameter, like if you are increasing the intensity of the laser, if you are increasing the integration time of the overall analysis or the number of accumulation, how these values are changing. In all the cases, if you are changing the condition, light condition was the dark, light, so all these cases, there are no more variation in the overall output. So we got a perfect data for the determination of eigenvalue of different edible oil. So that is comparable with the available technique also. For the next level, so we are thinking that in this all data we have performed in a commercial Raman spectrometer. So it cost around 25 to 30 lakhs. So our concern is why we can go for a low cost Raman spectrometer. Why we can fabricate our own system or homemade system. So that is our next concern. For that purpose, we made one Raman spectrometer by buying some components, optical components, and also with the help of some optical engineer, we have interdisciplinary team. So with the help of optical engineer, we aligned the Raman spectrometer, and we found some of the important chemicals using the homemade spectrometer, and also in the different combination, also the different combination of CO, SO, and we have successfully implemented the same data in the whatever the algorithm we are already developed. So this is the first part of how the Raman spectroscopy is used in the field of food diagnosis. Food diagnosis, for that purpose, I took one of the examples, that's edible oil. And moving to the second part, how the SERS that I already mentioned, that one surface enhanced Raman spectroscopy is effectively used the disease diagnosis. For that purpose, I am doing one example, that is creatinine sensing in artificial urine. So why creatinine? Creatinine, as you know, that is one of the important biomarker that indicates the healthy functioning of kidney. Suppose in the case of, we know that even serum creatinine and urinary creatinine, two types of creatinines are there. In serum creatinine, the levels are mentioned here, 0.7 to 1.3 milligram per deciliter in men, and also 0.6 to 1.1 milligram per deciliter in female. So this is varying actually. So if you are in your blood serum creatinine level is increasing, that means you have some kidney problem. In the case of urine, it is reverse only. If your creatinine levels in the urine is decreasing, that mention that you have some kidney or kidney malfunctioning. Okay. So how we can calculate, how we can estimate the creatinine in both the serum and the urinary sample? So currently we are using the colorimetric method, that is called the Jaffe's technique. For that purpose, what they are doing, they are mixing creatinine with the picric acid and some alkaline solution, that they are using NaOH. So what happened here, the creatinine picric, some colored complex will form. So based on the color, using the colorimetric technique, they are estimating the concentration of creatinine present in both serum and urinary sample. But the problem associated with this colorimetry or the wet chemical analysis, we can see here. So some of the non-creatinine chromogens also react here. So that will give some imprecise data. And in some cases, the stability of the old solution with the picric acid, then NaOH, the alkaline pH, those all are very important. So this is a purely a wet analysis, we can say. So the same concern I'm in the case of edible oil, I'm thinking here, why we can solid state. Okay, without using any colloidal silver nanoparticle, without using any colloids or without using any solution phase, why we can go for a effective method for the detection of creatinine in artificial urine or serum sample. So for that purpose, moving to that purpose, we have to create or we have to fabricate one SCRS substrate for the effective detection of this creatinine present in the sample or analyzed sample or artificial urine. For that purpose, here you can see that when there are three types of preparation methodologies are there. First one is actually the simple metal nanoparticle. I already mentioned that one. We can prepare this kind of metal nanoparticle either by physical or chemical methods. The second one is called actually metal nanoparticle. With a metal nanoparticle, whatever the aqueous nanoparticle we have, the colloidal nanoparticle we have, we can dip on the substrate or we can immobilize on a solid substrate, like using some method like inkjet printing, dip coating. And the third one, that is we are actually focusing, that is we are creating some nanostructure or microstructure surface on the substrate, and we are coating nano material. So as I already mentioned that one here, in the case of SCRS, the ideal property I mentioned in the previous slide, the ideal property, roughness is an important property. Suppose if you are going for discussing the SCRS property of a spherical nanoparticle and a nanostar, you can observe that one, the nanostar having higher SCRS activity compared to nanoparticle. It is because of their sharpened features. We can say that it's their sharpened feature. If you are going for a roughened surface also, you can see this kind of sharpened feature. That is an important factor that will influence the SPR property of nanoparticle also. So our current strategy is we have to make some roughened surface. So here you can see that it's a simple plain glass only, microscopic glass slide only. So we are creating some microscopic or nanoscopic surfaces above this glass slide using some method that is actually is a industrial method only, that is called abrasive blasting. This is a sandblasting instrument. This is mainly used for some dental application or some they are using the cleaning application. So here what is our aim? We have to create some clusters, these microscopic or micro structures or nanostructures on the glass surface. So finally we are coating these micro structures with the silver or gold or some plasmonic metals. Here for that purpose, we are using thermal evaporation technique. So we are prepared on SCRS substrate that is actually a roughened surface. This is our final aim. Actually, we need some sharpened features. In the sharpened feature, we have to incorporate our silver nanoparticle and finally the analyte molecule. So coming to the morphological analysis of this substrate, you can see that one here is the normal surface. This is the blaster surface. You can see more sharpened features in the blaster surface, and also we perform some of the analysis with the different types of beads. The MITS means sandblasting instruments, which means different types of sand we are used and the different sizes of sands we are used. So finally, we optimized all the data, all the blasting process based on the SCRS analysis, because which structure or which morphology we are getting maximum SCRS and which structure having maximum sharpened features. So here you can see that even the different this is the AFM images of sandblaster or sandblaster substrate coated with a different thickness of silver nanoparticle. So coming to the some studies of this substrate, you can see that this is the one of the XRD study. Here you can see this is a bare glass slide. This is the silver coated glass slide. This is nothing actually. We have just giving that one. The silver is clearly doped or clearly coated on the substrate surface, and here the UV spectra actually you can see that one. The silver nanoparticle coated around 40 to 50, 60 nanometer. As per the literature studies, also they are suggesting the nanoparticle having 40 to 60 nanometer. They are showing excellent SCRS activity. So the same data, if it is this in the case of 50 to 40 to 60 nanometer, we can see the maximum redshift of the SCRS. Maximum redshift of the UV analysis. That is mainly due to if the size of the nanoparticle is changing, their alignment in the surface also, their orientation in the surface, the sun branch surface also changing. And coming to the XCRS analysis, you can see here I coated with a different thickness of silver nanoparticle on the silver metal on the SCRS substrate or the sandblasted substrate. Here we can see the same observation. In the case of 40 to 60 nanometer, you can observe a maximum SCRS intensity that is accordance with the literature report. So coming to the stability study, their enhancement factor is one of the key point regarding the SCRS substrate. If it is having good enhancement factor, that we can use it for the purpose of any sensing. Okay, here you can see that intra and intraday stability studies, both the case we got a good stability for the substrate, and here for the sensitivity calculation we got around picomolar sensitivity for the estimation or determination of MPa, that is one of the Raman reporter molecule. All these things that is corresponds to the characterization studies of SCRS substrate. They are getting good stability, good uniformity, good reproducibility, good enhancement factor. So the next level actually, and also we analyze some of the important biomolecules, and also some dyes. Okay, some pesticide using the same SCRS substrate. We got good sensitivity for each chemicals. And the next level, our point is we have to develop one system or some device that we have to effectively sense the creatinine in artificial urine. For that purpose, we are already fabricated one SCRS substrate. So we are keeping one more plain glass slide above the surface. Okay, what the purpose actually? Here you can see that one. Here two holes I made. Here one is for the Raman analysis and another one for the incorporation of analyzed solution. If you are keeping like this, the surface normally if you are comparing the normal plain surface with the blasted surface, you can see that one there is maximum absorption rate of the analyte molecule, and also the most of the case we are using the analyte in water. So if you are dropcasting the water, you can see that to make a droplet. The droplet means you can see it's a lens structure. So that will also make some complication, the optical complication while we are performing any type of spectroscopical analysis. For that purpose also we made this one, and also the most importantly using while we are using that coating process, the silver nanoparticle coating using the thermal evaporation, we are heating the substrate. So we can observe that maximum absorption, or we can say the adhesive property, not adhesive property, we can see the maximum absorption of the metal nanoparticle on the surface we can observe. So that will enhance the reusability of the substrate. For example, we can use the same substrate for 10 to 15 analyses. Okay, after proper cleaning with the water. So I already mentioned that when water has negligible effect on the Raman spectral analysis. So coming to the next part, this is the Raman spectral analysis of creatinine. You can see that even various Raman signals for creatinine. And the next level, what we did here, we added creatinine in a water system. So different concentration of creatinine is intentionally added in the water system. You can see that one, the peaks of creatinine is increasing. The important peaks of creatinine is increasing with the increasing of concentration of whatever the analyte we are added here. And here you can see here the creatinine artificial urine. Okay, the major component of the major component that is present in artificial urine, you can see that urea. So if you are taking the simple artificial urine Raman spectra, you can see only the peak of urea. Okay. So if you are adding intentionally the different concentration of creatinine to the artificial urine, here you can see that even to the creatinine peak, if the concentration is increasing, the peak of creatinine is also increasing. So our next important aspect is how we can develop some similar to our first work, the edible oil work, how we can develop some algorithm based on this one. So for that purpose, what we did here, the peak of urea is almost constant for all cases. So which one is varying? The important peaks of creatinine is varying, but in this analysis we didn't take this part actually, the peak at the peak between 1200 to 1500, because we are bare substrate is actually glass based. So it is showing some peak at 1200 to 1500. So our major analysis part is going to the next level. That is actually we took the peak at 683. Here you can see that one, the 683 Raman spectral analysis of peak. So for that purpose, we took the different concentration of creatinine and plotted a graph with the intensity at 683, and also we took the same concentration of creatinine and we plotted a graph at intensity at 999 centimeter. That is the peak of urea. Here you can see that even the most of the case the intensity is same, but here it is linearly increasing. So what we did, we took the ratio of these two, so we get a linear plot. Okay, from this plot we got a straight line equation also. That straight line equation exactly matching with whatever the concentration. Here you can see that one we took the peak ratio at 683 and 999. So we got the slope as well as intercept of the same straight line equation. And also here you can see that one we did the same analysis to two blind sample. From the blind sample we observed that one both whatever the concentration we have prepared, that is accordance with the blind sample concentration, whatever the predicted value using the our this straight line equation. So our next level is actually we have to develop an algorithm based on this one. Or before that we have to validate also. So validation, for the validation purpose, what we did some HPLC analysis with the different concentration of creatinine in artificial urine. So we observed that even this is our HPLC value, and this is our whatever our reported value using our developed methodology or the straight line equation. So here you can see that one very less relative error compared to so here you can see the very less relative error in the both the case, whether it's the first blind sample, you can see that's a 13.6, and second it is around, the second means actually it is predicted by HPLC method, it is 14.4. Okay. So coming to the summary of the work, so I started with this analytical aspect of chemistry actually. So how we can use the Raman spectroscopy for the effective detection of iodine values from edible oil. And the second part is actually how we can use the surface enhanced Raman spectroscopy or SERS substrate for the effective detection of creatinine sensing. So these are the points regarding that. We successfully developed the method, one method, and also we implemented the method, our handheld spectrometer also, for the effective detection of iodine value present in edible oil. And the second work, what we did actually, we developed one SERS substrate and we successfully incorporated this SERS substrate for the effective sensing of creatinine that is present in artificial urine. And finally, coming to the acknowledgement, I really acknowledge my team at CSIR, NIST, and also my team at MITS. Thank you.